Yeehaw, Gen Chem 1. Can you believe we've survived this journey? This is our last new content video. Oh my word. We survived this together. I love it. I hope you enjoy it. We kind of saved the best for last. I'm just going to do 4 problems in this video. We're going to continue with our gas laws. Only this time we're going to take our gas laws and we're going to apply them to chemical reactions. This is going to be so fun. You know, in this last unit, we have a little bit of every unit before it, so it's really awesome. In this one, we're going to take everything we did in Unit 3, and we're going to apply it in our chemical reactions. But this time, notice that we have gases. I got a fierce dog in the background, sorry. And so this is going to be so much fun. So the first thing you want to take a look at in your reaction is the fact that you actually have gases in your reactants in your products. Now we've got 1 solid and we've got 3 gases. So anytime you've got a gas in your chemical reaction, if you're calculating anything with your gas, we've got to keep in mind our ideal gas law. And let's actually just write it right. Okay, PV equals nRT. And that's always, we can apply that for our gases. So let's take a look at the problem and let's follow what we kind of did in our last examples and that last video. You know, I like to take and just literally just start. I notice those gases and I'm just going to start to spell out my gas law. And then let's see where we can apply it. Now, why I love this section is, like I said, we get to apply a little bit of Unit 3 on here. So we did not forget our yoga pants and our candle. Let's light that candle and find some balance. We can't do anything until we balance this reaction. And actually, if I take a look at it, shut the front door, I think we just got a free pass. Doesn't this look balanced already? I think it is. Okay, awesome. So we are all balanced 1-to-1 on everything. So don't forget, we still have trust issues. We have to balance our reaction. And then I'm going to go ahead and start to read the problem. Okay, how many liters of hydrogen? All right, so let's combine a little Unit 3 and a little Unit 4. I'm going to put a little question mark over hydrogen. And then we're looking at the complete reaction of 15.7 grams of carbon. So let's go ahead and write that up there. So that's kind of fun. We're starting with that solid. And then what we're trying to solve for then is our hydrogen, which is a gas. So assume the hydrogen gas is collected at a pressure of 1 atmosphere. And we're already in atmospheres. That's awesome. And a temperature of 355 K. I love it. Already at 355 K. Let's go ahead and fill in what we know. We're being asked to calculate volume, and then we know our gas constant already. Liters, atmospheres, moles, Kelvin. Okay, so our units are good, and now we've got 2 missings. Or do we? The question's asking for volume. What are we going to do about moles? Well, this is the fun part. We combine Unit 3. We know this. Y'all can do this in your sleep. We're going to take that 15.7 grams of carbon and we're going to convert it to moles of hydrogen. Okay, we know how to do this. We've got our carbon solid. Let's go ahead and convert that to moles. I'm going to go ahead and just round and use 12. And then I'm going to convert that using my mole ratio. Okay, so we've got 1 mole of our carbon to, I guess, 1 mole of our hydrogen gas. Okay, well, that was nice. All right, grab your calculator. Let's do it. 15.7 grams of carbon. Turns out that's 1.31 moles of hydrogen gas. Perfect. So all we did in this problem to then use our chemical reaction was we just recognized that in Unit 3, we dealt with solids and liquids, okay? And we can combine that, and then now we just added the fact that one of our products is a gas. So if we're going to solve for how much hydrogen we make, well, we're going to solve for that in terms of volume in our gas. And so we need to use our ideal gas law anytime you've got a reactant or product that's a gas, but you can still convert to moles if you have grams of a solid. So we just combine two concepts there. So now what do? We put that 1.31 moles of hydrogen right over here. And now this is exactly like what we've done in our last video. So let's plug and chug. Let's take and solve our PV equals nRT, and let's solve that for V. Okay, and then let's just plug and chug. I love it. Let's put in our, oh, you know what? I learned in the last video to give myself some space. So let's start over here. Our moles, 1.31. Okay, our constant. Oh, not enough space. Dang it. Okay. And then our temperature. And then all divided by our pressure. All right, remember we double check our units, moles, done. Atmospheres, gone. Kelvin, gone. And we're left with liters. All right, so let's grab your calculator. Let's do this. 1.31 times our gas constant times our 355 divided by 1. I'm getting 38.2 liters of hydrogen gas. Oh, that needs a sparkle pen. Okay, don't you love it? The only thing that would make this problem even better is, let's say we put in naming or something for your reaction. What? Wouldn't that be so much fun? All right, I feel like let's do another one of these. We're sort of combining our Unit 3 and our Unit 4. Let's try another one. All right, we've got a nice reaction here. We've got, this time, aluminum and oxygen making aluminum oxide. All right, we already know from Unit 3, before we do anything, let's find our balance. This one is not balanced, so let's start with that aluminum. Let's see what we can do. And then, crap, we have, our aluminum's fine, but we have 3 oxygens, so in theory, that would be 3 halves. And you know, we don't really like to leave a fraction, so I'm gonna have to multiply everything by 2. So let's go ahead and make this 4. This one is 3, and this one is 2. All right, now we should be totally balanced. I love it. All right, and then I notice we've got solids and gases mixed again. So if we're solving at all for oxygen, we need our PV equals nRT. And of course, we're going to look for oxygen. So I'm going to go right ahead and spell out this one. And then, okay, we're already being told we're solving for volume. And then let's just start to fill in what we know, right? I've got 782 millimeters of mercury, that's a pressure. All right. We already know we need to convert that to atmospheres, so we'll just write that out. 25 degrees Celsius, let's put that in. We know we're going to need to convert that to Kelvin. Okay. And then we've got, oh, this is fun. We're starting with a solid again. We've got 52.8 grams of aluminum. And then we're being asked oxygen. Okay, perfect. So what do we do then? We know R. All right, let's put in R. And then we're gonna need to get N somehow. And we're going to do that exactly like Unit 3, just like our last problem. We're given grams of aluminum, and let's convert that to moles of oxygen. So we're literally going to take those grams of aluminum and convert to moles of oxygen. Okay, let's start it. We've got 52.8 grams of aluminum. And we're going to need to convert that to moles. Grab your periodic table. I've got to look at mine. And I've got 27 grams per mole for aluminum. And then let's use our mole ratio. We've got aluminum to oxygen. All right, what are we going to fill in there? I've got 4 moles of aluminum to every 3 moles of oxygen. So what are we going to get then for our moles of oxygen? Grab your calculator. Let's do this. Divided by 27 times 3 divided by 4. Oh, fierce dog again. I've got 47 moles of O2. Okay, awesome. Doesn't it feel good when you get towards the end of this semester and you actually start to combine stuff? Because you get a little sassy, but then you realize it's kind of 2 for the price of 1 because we already learned some of this stuff. So awesome. All right, so now let's plug in. Again, we've got our ideal gas law. We're going to solve for volume. So we're going to rearrange. Okay. And then let's start to plug that in. All right, let's plug and chug. What did we get for our moles? We got 1.47. We've got our constant. And our temperature. Oh, son of a motherless goat. We didn't unit convert. All right, 273 plus 25, what do you get? This is typically 298 is standard room temperature in Kelvin. And then what about our pressure? We need to convert that to atmospheres. Let's take a second to do that. 782 millimeters of mercury divided by 760 will give us atmospheres. So grab your calculator there. 782 divided by 760. I get 1.03 atmospheres. How does that sound? Okay, 1.03 atmospheres. Let's double check our units. Okay, moles done, Kelvin done. We are left with liters, and let's plug all this in, and let's see what we get. 0.08026 times 298 divided by 1.03. I am getting 34 point, I guess, 131. And we can round that in liters. Oh, isn't that fun? I love it. All right. Really, I kind of love the gas laws. It's such a good way to end this semester because you really just feel like you're doing this complicated problem. But as long as you can keep track of what goes where, you really just kind of plug and chug into your equation. I kind of dig it. Now, you know we can't end right here. We've got to do a little bit more. I've got 2 more problems. I'm going to show you the nice version, and then we have to leave on a good note, and we've got to get sassy. So let's do the nice version of this problem, and then I want to show you what the mean version of this problem looks like. We're going to turn right around and solve it again and get sassy. And I'm going to take 1 second to go get my dog. Rocky, hey, come on. Get in here. Thank you. You're so fierce. Come on. Okay, sorry, you guys. I'm so sorry that's in the middle of your video. I guess that's life at home, right? I'm sure y'all have all kinds of distractions at home as well. Okay, so let's take a look at our problem. We've got a nice combustion reaction. Shut the front door. We've seen these before. I love it. Oh, what just no, sir. Thank you. What is happening here? We have got all gases. What? Okay, so this is where it gets fun. Everything in here is a gas. Now, this first one is nice because check this out. My eye goes straight to STP. And why do we care about STP? Whenever you see that you are at STP, we get a shortcut. And that shortcut is a unit conversion from Avogadro. Thank you, Avogadro. That shortcut is 22.4 liters of gas is a mole. And remember, this is awesome because it's any gas. So this is awesome. All right, let's take a look at our question then. How many liters of water vapor is formed? All right, done. Putting my question mark right there. From the complete reaction of 10 liters of methane. All right, 10 liters right there. Assume that your steam is collected at STP. Okay, so this is still gas laws in Unit 3 combined, only, look at what we're starting with, liters and not grams. So if you are at STP, you get to use this as your unit conversion. And then we can go to moles of our water. So let's take our 10 liters of methane. That's what we're starting with. Let's convert that to moles. We've got moles of methane. Every 1 mole is 22.4 liters of gas. And then let's convert that. Oh, wait a second. We need a mole ratio. We got so excited by this problem. What did we forget to do? Balance. So let's double check our balance. We've got 1 carbon, 4 hydrogens, so I needed 2 there. And then we needed 2 there. Okay. So, right, we've got 4 oxygens. Yep, we're good. All right, so now let's put in our mole ratio. We've got 1 mole of methane for every, 2 moles of water. So now how many moles of water are we going to end up with? Let's just pause and solve that one. We've got 10 liters divided by 22.4 times 2. I am getting 0.89 moles of steam, of water. Okay, I love you. I love it. All right, so now this is awesome because we get to turn right around and use our unit conversion again and solve for liters of water vapor. What? This seems like cheating because we haven't even used PV equals nRT. All right, let's take our 0.89 moles of water and let's convert it to liters. And that is for any 1 mole of gas. All right, let's take our 0.89 times 22.4. And I get 19.9 or pretty much 20 liters of steam. See how that STP is such a shortcut? I love it. All right, you've got 1 of these or 2 of these in your homework. So if you spot that STP, your problem just got pretty nice. You don't even need the ideal gas law. You're really using what we did in Unit 3. You are just getting a new unit conversion. So how do you recognize when can you use it when you are at STP? And then how do you recognize, well, why can't I just use the molecular weight of methane? Because you're not in grams, you're in liters. Okay, that's how you can tell the difference between those. Okay, now I promised you we're going to end on a sassy note. So let's take this same problem and let's make it mean. Woo! Let's do it. All right, we've got our same problem. Let's not even read it yet. Let's not forget to balance like we did on the last one. Let's put our balance in there. All right, let's make it mean. How did we make it mean? We are not at STP. So let's read what we're given. We're asked our liters of water again. Put a question mark right up there. And we are given 10 liters of methane. Okay, same amount right there. But now check it out. We are at a pressure of 1.1 atmospheres and a temperature of 445 K. That is not at STP. So it's not that this problem's mean, it's just long. And why is it long? Okay, let's follow what we would do in Unit 3. We would take the one amount we're given, 10 liters of methane, and our goal is to convert that to water. But here's the kicker. This is liters, not grams. So I can't use our standard conversion to moles by using our molecular weight. It doesn't work here. We have to do it in another way. And we're not at STP, so we can't use that. So shut the front door. How are you going to convert liters to moles? PV. If I could write halfway decent, this would be halfway good. Okay, PV equals nRT is the only way we're going to be able to convert that 10 liters of methane to moles. What? You heard that right. So let's start to spell it out. Take a screenshot for a second. I am going to erase here and write my PV equals nRT. All right, so what is our goal? We've got 10 liters of methane, but what we need is moles. So let's start to spell out what we know. And let's hope we're just missing moles. All right, so we are looking at 10 liters of methane. We are at 1.1 atmospheres. Our temperature is 445 K. Oh, let's not forget a number. And we know this constant. And then what are we missing? Moles. I love it. So let's take our PV equals nRT and let's rearrange it for N. And let's plug in. All right, so what is our pressure? 1.1. What's our volume? 10. Okay. Our constant. Takes me a little bit to write that out. And then our temperature. Wow, how do you make this truly mean? You put a bunch of unit conversions in here. All right, let's grab our calculator and let's figure out our moles. Okay, let me grab my calculator. And remember your order of operations on this one. All right, I am getting 0.3 moles of methane. Okay, now this is awesome. This is a great place to start, but we are not done. We now have our moles of methane, but our question is asking for water. So what do we do with the moles of methane? Well, we needed to convert it to moles of water. So let's convert that then. Let's use our mole ratio. And let's see, moles of water. And then we found our balance. So what did we have? 1 to 2. So I'm going to go out on a limb here and not use my calculator. And I'm going to get 0.602 moles of water. Okay, now that may be a mistake, but let's do it. Okay, so now, I love it. So now can I just multiply by 18 the molecular weight? I've got my moles. Let's write it up here. We've got our moles of water. And now we need to go to, oh, son of a motherless goat, liters, not grams. So how do we convert moles to liters? And we are not at STP, and we can't use our molecular weight. We have only one option, and that is PV equals nRT. So this problem is truly 2 for the price of 1, because guess what? We get to turn right around and solve for liters in our gas law. Okay, let's do it again. I love it. All right, we do get to use some of the same. This is a reaction all happening at the same time and the same conditions. So our pressure is still 1.1 atmospheres. Our temperature is still 445 K, same constant. Okay. And we just got our moles. That's our 602. So let's put that in. That is for our steam. And then now we get to solve for volume. Okay, that's cool. We've done that before. So let's rearrange our PV equals nRT. Let's solve for volume. All right, now I think I'm running out of some space, so I'm going to have to solve that down here. And I may have to scroll to look for those numbers. All right, I think I remember our moles here, 602. And then our gas constant. And then temperature. All divided by, I think it was 1.1 atmospheres. Quick, let's just do some canceling here. Perfect. Okay, grab your calculator, let's do it. 0.602 times 0.08 times 445 divided by 1.1. I get, again, look at that, 19.98 liters of water. Not a big difference between the two problems. But why did I have to go through that whole solution? Because we were not at STP. And so your conditions can be all over the place, but actually 1.1 atmosphere isn't that different from 1 atmosphere. So we can expect that's pretty close. And a temperature of 445 K, that's certainly higher than 273 K. So our answer should be slightly different, but surprisingly, it's not that different. So we still need to do this whole solution using 2 PV equal nRT solutions. I love it. All right, so I think I've started with nice problems and I've ended with the worst of the worst. So now I think you can tackle all of your homework, and I will be posting this video today and then posting your